Picture this. It's the Cold War, paranoia is running rampant, and the Department of Defense needs a communication system that could survive, well, practically anything, even a nuclear attack. That's where ARPANET comes in, the granddaddy of the Internet.
Makes sense. Can't rely on a single point of failure when you're worried about mushroom clouds, right? But I saw this excerpt mentioning UC Berkeley. Weren't they all about, like, peace and love, not exactly known for their war games?
Right, but that's where things get really interesting. See, a lot of the heavy lifting for TCP/IP, it didn't happen in some top-secret bunker, but on the sunny campus of UC Berkeley. They were working on this thing called the Berkeley Software Distribution, BSD, and they ended up playing a key role in developing, and get this, sharing TCP/IP.
Sharing, as in, hey world, here's the blueprint for this super resilient network protocol. Feel free to use it.
Just like that, pretty much. Yeah, it was basically share to share, where spread to universities, institutions, everywhere. Talk about turning swords into, well, network cables.
That's amazing. So this Cold War relic is what allows me to effortlessly stream cat videos today. Amazing. But let's zoom in on how it all actually works. The study guide you sent mentions these models, the DOD model and the OSI model, layers upon layers of networking lingo. It's a lot.
Think of it like a cake, all right? Each layer has a purpose. The DoD model, that's the one we're focusing on here, keeps it nice and simple. 4 layers. You've got the process application layer at the very top, that's where all the action happens. Web browsers, email clients, you name it, they all hang out up there.
Okay, so if I'm browsing the web, checking email, downloading a file, that's all happening at the application layer.
Exactly. And each of those applications, they rely on specific protocols to communicate, like HTTP for browsing the web or FTP for file transfers.
Speaking of FTP, you mentioned downloading a large file earlier. Remember the days when that was the way to move big files around?
Oh, absolutely. Before cloud storage took over the world, FTP was the lifesaver. Can you imagine emailing a 50 GB file? But I do remember some frustrations, shall we say, with Telnet. Another one of those protocols, like, it felt very Wild West in terms of security or lack thereof.
That's putting it mildly. Telnet, it transmitted everything in plain text, passwords, everything, just out in the open, a hacker's dream. That's why SSH, Secure Shell, came along, providing that encrypted tunnel for remote access that Telnet so desperately needed. Right? Makes sense. So we've got all these different applications, each using their own protocol, all wanting attention at the application layer. How do our computers keep it all straight? It's like a party where everyone's speaking a different language. Chaos.
And that's where port numbers swoop in to save the day. Imagine a busy office building, hundreds of employees. You wouldn't want all the mail going to just one mailbox, right? Port numbers, they're like those individual mail slots, each assigned to a specific application or service. They make sure the data gets delivered to the right place.
So it's like having a unique address within a device. That's pretty clever. The study guide mentions these things called well-known port numbers, like port 80 for HTTP. Are those standardized across the entire internet?
Absolutely. There's this organization, the Internet Assigned Numbers Authority, or INA. They maintain a list of these well-known ports. That's how your browser knows to use port 80 for HTTP, your email client knows to use port 5 for SMTP, and so on. It's like a universal agreement on who gets which communication channel.
So a single computer can have multiple applications all chatting away on the network at the same time, each using their own designated port number.
That's incredible. Yeah. But, okay, so the application has its data all packaged up. It's got its port number stamped on it. Now what? How does it actually get delivered across the network?
That's where we descend to the next layer of our cake, the transport layer. And here's where we meet our two trusty sidekicks, TCP and UDP. They're like the delivery services of the internet. TCP and UDP. I always get those two mixed up. One's like the reliable mail carrier. The other's more free-spirited messenger, right?
You got it. TCP, or Transmission Control Protocol, it's all about reliability. It wants to make absolutely sure your data arrives in order and in one piece, even if it has to resend those packets multiple times.
Okay, so for something like downloading a huge file where you absolutely need every single bit to be correct, TCP would be the way to go.
Exactly. It's like sending a package with cracking and insurance. Might be a tad slower, but you know it'll get there safe and sound.
Yeah.
UDP, on the other hand. UDP, or User Datagram Protocol, it's all about speed.
What about situations where speed is more important than getting every single bit perfect?
That's where UDP really shines. Think real-time applications like video conferencing, online gaming, that sort of thing. A little bit of data loss here and there, it's not the end of the world. But delays, buffering. Now, that's annoying. UDP keeps things moving smoothly, even if it means sacrificing a bit of data integrity along the way.
Interesting. So depending on the situation, either TCP or UDP takes over at the transport layer, adding their own, shall we say, flair to the delivery process. But once our data is packaged and ready to go, how does it actually navigate the vastness of the internet, find its way through that digital jungle?
Buckle up.
Yeah.
Because that's where we enter the world of IP addresses and the internet layer, the true highway of the internet.
Hit the information superhighway. I'm ready.
IP addresses.
IP addresses, those strings of numbers we see everywhere online.
IP stands for Internet Protocol, and its main job, it's like a global addressing system for devices on the internet. Every single device, it needs a unique IP address to send and receive data. Think of it like a home address, but instead of streets and cities, we have networks and subnetworks.
Okay, so IP addresses, they're like unique IDs for devices on the internet. The study guide mentions they're 32 bits long, usually written in that dot decimal format like 192.168.1.1. But it also mentions that each IP address, it actually has two parts, the network address and the host address. What's that all about?
Good catch. Think of it like this. The network address, that's like the zip code, it identifies a specific network or subnet. The host address, that's like the house number within that zip code, it identifies a specific device on that network.
So all devices on the same network would share the same network portion of the IP address, and then each device would have its own unique host portion, right?
Exactly. That's how networks are structured and organized logically. And to manage this whole vast network of networks, we have different classes of IP addresses, A, B, and C. Each one is designed to accommodate networks of different sizes.
So a massive corporation with thousands of devices, they'd need a Class A network, while my humble little home network could probably squeeze by with a Class C.
Precisely. Like the difference between a bustling metropolis and a quiet little cul-de-sac. Class A networks, those are reserved for the big players. Class C networks are perfect for smaller setups. And Class B falls somewhere in between.
This whole system of IP addresses, network classes, subnet masks, it's like the invisible infrastructure that makes the internet even possible in the first place. It's mind-boggling how much complexity is going on behind the scenes every time I open a web page or send an email.
And we've only just scratched the surface. There are also these things called private IP addresses, used within local networks like your home or office. They're like those secret phone numbers you only share with close friends and family.
Secret phone numbers for devices. Intriguing. But if these private IP addresses are hidden away within local networks, how do they ever communicate with the outside world? It's not like you can send a letter to a secret address.
That, my friend, is where NAT comes in, Network Address Translation. Think of it as a sophisticated receptionist, carefully managing communications between the private network and the public internet.
So NAT, it acts as like a gatekeeper, allowing devices with those private IP addresses to access the internet without revealing their true identities to the outside world.
Precisely. It's a fascinating topic, really. Deserves its own deep dive, to be honest.
Uh-huh.
But for now, just know that NAT plays a crucial role in conserving those precious public IP addresses and adding an extra layer of security to our online interactions. We've got broadcast addresses, unicast addresses, and multicast addresses, each with its own role to play in the grand scheme of network communication.
Okay, let's start with the obvious one. Broadcast addresses. Sounds pretty self-explanatory. It's like sending a message to everyone on the network all at once, right?
That's it. Imagine you're at a party and you shout out a message to the entire room that's essentially a broadcast address. It sends data to every single device on the network.
So if I wanted to send a message to every device connected to my home Wi-Fi, I'd use a broadcast address.
Precisely. Useful for things like, network-wide announcements or discovering devices on a local network.
Yeah.
But routers, those traffic directors of the internet, they usually step in and prevent broadcasts from going beyond their designated networks.
Makes sense. Otherwise, the internet would be like one giant shouting match, everyone trying to talk at once.
Exactly. Now, on the complete opposite end of the spectrum, we have unicast addresses, the workhorse of, everyday internet communication.
Unicast, one-to-one communication, right? Like sending a private message instead of shouting to the whole room.
You got it. Every time you send an email, browse a website, stream a video, it's unicast addresses diligently shuttling those data packets back and forth between your device and the server.
So safe to say that most of our online interactions rely on the quiet precision of unicast communication then.
Absolutely. It's how we manage to have those individual conversations amidst the constant hum of internet traffic.
Mm-hmm.
And then we have multicast addresses. They kind of fall somewhere in between broadcast and unicast.
Multicast. That sounds intriguingly specific.
It is. Multicast lets you send data to a specific group of devices, ones that have actually, signed up for it, expressed interest in receiving that data. It's like joining a mailing list. You'll only get the messages that are relevant to that group. No need to blast everyone on the network.
So like if I was playing an online game, the game server could use a multicast address to send updates only to the players in my specific match. No need to send it to everyone playing the game, right?
Exactly. Streamlines group communication. No need to flood the entire network with unnecessary data. You mentioned earlier how amazing it is that we can just type in a domain name like google.com and magically end up at the right website.
It's true, I've always kind of taken that for granted. Our computers, they can't just magically know the IP addresses of every website out there, can they?
That's where the magic of DNS comes in the domain name system. Think of it like the internet's phone book.
So instead of names and phone numbers, DNS maps those domain names like google.com to their corresponding IP addresses.
Precisely. You type in a domain name, your computer sends off a request to a DNS server. Hey, what's the IP address for this? The DNS server looks it up in its massive database, sends back the answer, and boom, your computer can establish a connection.
It all happens so seamlessly. It's really quite incredible. I type in a name and, like magic, I'm whisked away to my online destination.
It's a testament to the power of having these standardized protocols and, of course, the brilliant minds who designed this amazingly complex yet elegant system.
I never realized how much intricate machinery is working tirelessly behind the scenes every time I open a web page or send an email.
It really is fascinating, isn't it? Like peeking under the hood of a high-performance car, all these complex parts working in perfect harmony.
Exactly. And to think it's all built on this foundation of TCP IP, this Cold War relic that's still going strong all these years later. We've covered a lot of ground today, from the history of TCP IP to the different types of IP addresses, the role of DNS. I feel like I can navigate the online world with a newfound appreciation for how it all actually works.
Knowledge is power. And understanding the fundamentals of networking, well, that opens up a world of possibilities.
You said it. A huge thank you to our expert for shedding light on the often mysterious world of TCP/IP. And to our listeners, keep those curious questions coming, and we'll see you on our next deep dive.